Somewhere around 130 light years from Earth, there's a planet that should not exist. Not because it is too small, or too strange, or too far away. It should not exist because of simple, well-tested physics. For decades, scientists believed that any rocky planet growing past a certain size would stop being G-rocky. It would grab huge amounts of gas from the space around it and turn into something like Jupiter, a giant ball of gas with no solid surface at all. That rule has held up again and again in system after system for years, and it became one of the quiet, trusted foundations of how astronomers think about planet formation everywhere in the galaxy. Then astronomers found a planet 23.5 times heavier than Earth, and it is still, somehow, mostly solid rock. This is the story of that planet, why it should not be possible, and what scientists think actually happened to create it. Let's start with the basic facts, because they are strange enough on their own before we even get to the mystery. The planet is called GJ 523b. It orbits a small, cool star, closer to that star than Mercury is to our Sun, completing a full orbit in just under 18 days. Now, that alone tells you something about the environment this planet exists in. A full year on this world lasts less than 3 weeks, and its surface almost certainly bakes under a level of heat and radiation nothing in our own solar system experiences. The planet is roughly 2.5 times wider than Earth, and it weighs about 23.5 times as much. Sit with those two numbers together for a moment, because that is where the real strangeness begins. A planet only 2.5 times wider than our own should not be anywhere near 23 times heavier. Something about that combination of size and mass is deeply unusual. Here is the number that actually shocked researchers. Its density works out to roughly 127 grams packed into a space the size of a cubic inch. To put that in a way that actually means something, that is far denser than almost any large planet astronomers have ever measured, and it tells scientists something very specific. This is not a gas planet with a small rocky core buried somewhere inside it. This is a planet made almost entirely of solid material, all the way through, compressed under gravity far stronger than anything found here on Earth. Astronomers have a name for planets like this. They call them mega-Earths, and until recently this was mostly a theoretical category, a term scientists use to describe what a planet like this would look like if it existed, without actually having a clean, confirmed example to study closely. GJ 523b changes that. One researcher involved in confirming the discovery described it as the concrete blueprint scientists had been waiting decades to find. The first time this category of planet has been measured with enough precision and confidence to move from theory into confirmed reality. So why does a giant rocky planet break the rules astronomers had built their whole understanding around? To answer that, you need to understand how planets normally form in the first place. Young stars are surrounded by a spinning disk of gas and dust, the leftover material from the star's own birth. Over time, tiny particles in that disk collide and stick together, forming small rocks, then bigger rocks, then planet-sized cores, a slow process that can take millions of years to unfold. As a rocky core keeps growing and picking up more material, it also grows a stronger and stronger gravitational pull, reaching further out into the surrounding disk with every added layer of mass. Here is where the established rule comes in. Once a growing rocky core reaches somewhere around 20 times the mass of Earth, its gravity becomes strong enough to start pulling in huge amounts of hydrogen and helium gas from the surrounding disk. Once that process starts, it tends to run away quickly. The planet keeps grabbing more and more gas, wrapping itself in a thick atmosphere, and within a relatively short time, in astronomical terms, it turns into a gas giant, similar to Jupiter or Saturn in our own solar system. This is not a fringe idea. It is one of the more well-tested, widely accepted models in modern planetary science, built from decades of observing how planets form and confirmed across many other star systems already studied. That is the rule GJ 523b appears to have broken. It sailed past that 20 Earth mass threshold, the exact point where growing planet is supposed to start turning into a gas giant, and it kept its rocky, solid structure anyway, holding on to only a thin, faint atmosphere instead of a thick, heavy one. It crossed the line every model said it should not have been able to cross without transforming into something else entirely. This is the first real turning point in the story because it raises an obvious question. If the physics says this should not be possible, then either the physics is incomplete or something unusual happened to this specific planet that scientists have not fully accounted for yet. Before looking at the possible explanations, it is worth understanding exactly how astronomers found this planet and confirmed these numbers, because the process itself matters for how confident scientists actually are in the result. This was not a single lucky observation. It was the product of multiple independent instruments, each confirming a different piece of the puzzle. GJ523b was first flagged by NASA's Transiting Exoplanet Survey satellite, a spacecraft that searches for planets by watching for tiny, repeating dips in a star's brightness caused when a planet passes directly in front of it from our point of view. That method can tell scientists how large a planet is based on how much light it blocks as it crosses in front of its star. But size alone does not tell you what a planet is made of. A large planet could be a light, puffy gas giant, or it could be a smaller, extremely dense rocky world. And from the transit data alone, those two very different possibilities can sometimes look surprisingly similar. To figure out which one you're actually looking at, you need to know the planet's mass as well as its size. That is where a research team led by astronomer Max Croft at the University of Wisconsin-Madison came in. Using a specialized instrument on the WIN telescope in Arizona, the team measured the tiny gravitational wobble the planet causes in its star as it orbits, a technique that lets scientists calculate mass with real precision by watching how much a planet's gravity tugs its star back and forth. Combining that mass, measurement with the size already known from the transit data, and adding further observations from the James Webb Space Telescope, the team calculated both the planet's true mass and its density with enough confidence to submit their findings for formal scientific review. So the mass is not a rough guess. It comes from two independent types of measurement, cross-checked against each other, which is exactly why this discovery is being taken so seriously, rather than dismissed as an unusual data error or fluke in a single instrument's readings. Now here's where the story escalates, because the planet's age turns out to matter just as much as its size. The GJ523b system is estimated to be only about 170 million years old. In the timeline of the universe, that is remarkably young, barely a blink compared to our own solar system's 4.5 billion years. To put that in perspective, dinosaurs were already walking the Earth by the time this planetary system was forming. That youth turns out to be a critical clue because it means astronomers are looking at a planet in a relatively early stage of its life, not one that has had billions of years to slowly lose an atmosphere it once had through some long, gradual process. This detail forced researchers to consider two very different explanations for what they were seeing, and it is important to separate what is confirmed from what remains an open scientific question. Because this is exactly the kind of story where speculation and confirmed fact can easily get blurred together. What is confirmed is the planet's mass, its size, its density, and the fact that it is overwhelmingly rocky rather than gaseous. These numbers come from real, cross-checked measurements published for scientific review. What is not yet confirmed, and is still being actively debated by the research team, is exactly how the planet got that way in the first place. The first possible explanation involves the planet's incredibly close, hot orbit, sitting nearer to its star than Mercury sits to our Sun. GJ523b is blasted with intense heat and radiation every single day of its short 18-day year. One idea is that any thick K-gas atmosphere the planet once had could have been slowly stripped away by that radiation over time, boiled off into space particle by particle, leaving behind only the dense rocky core we see today. Under this explanation, GJ523b may have started life looking more like a typical gas-rich giant planet, before losing its outer layers entirely under the relentless heat of its own star. The second explanation is more dramatic and in some ways more interesting to picture. Researchers have proposed what they call a giant impact scenario, the idea that GJ523b was not born this way gradually, but was instead created suddenly through a violent collision between two large rocky protoplanets earlier in the system's young history. Under this idea, when those two massive bodies smashed together, their dense rocky cores merged into one, while the lighter, gassier outer layers were blown away entirely in the impact, scattered back out into space. It is a scenario similar in some ways to some theories about how our own moon may have formed billions of years ago, but a far larger, more extreme scale, involving planet-sized bodies rather than a smaller impactor striking a young Earth. Both explanations remain genuine possibilities, and researchers have not yet determined which one, if either, actually explains what happened at GJ523b. This is exactly the kind of open question that real, honest science leaves open rather than forcing into a tidy, confident answer before the evidence fully supports one. It would be easy for a headline to simply pick the more dramatic explanation and present it as settled fact. The actual research team has not done that, and neither should the rest of us. So why does any of this actually matter beyond one unusual planet around one distant star? Because planet formation theory is not just about explaining strange individual worlds. It is the foundation scientists use to understand how planets form everywhere, including, eventually, how a planet like Earth came to exist in the first place. If the 20 Earth mass boundary, the point where a growing rocky planet is expected to inevitably become a gas giant, can genuinely be crossed under the right conditions, then that boundary is not as fixed and absolute as scientists previously believed. It becomes a general tendency rather than a hard, unbreakable rule. And that is a meaningfully different way of understanding how planetary systems actually behave. That distinction matters enormously for how astronomers search for potentially habitable worlds around other stars. Rocky planets are generally considered more promising candidates for life, as we understand it, compared to gas giants with no solid surface at all for anything to stand on. If massive rocky worlds like GJ 523b can exist in more situations than previously thought, it widens the range of planets astronomers might need to consider when searching for places life could theoretically take hold, even if GJ 523b itself, sitting far too close and far too hot to its star, is almost certainly not a habitable world in any meaningful sense. Its value to science is not as a candidate for life. It is as a working example of just how flexible planet formation can actually be. It is worth being clear that GJ 523b is not the very first mega-Earth ever proposed. Back in 2014, astronomers at the Harvard-Smithsonian Center for Astrophysics announced an earlier candidate, a planet called Kepler 10c, weighing about 17 times the mass of Earth, which researchers nicknamed the Godzilla of Earths at the time, a name that stuck in public coverage of the discovery for years afterward. What makes GJ 523b different and arguably more significant is both its size, at nearly 24 Earth masses, considerably heavier than that earlier candidate, and the strength and precision of the modern measurements confirming it, combining data from multiple advanced instruments in a way researchers describe as finally giving them a clear, confirmed blueprint for this entire category of planet, rather than a single uncertain example resting on more limited data. It also raises a broader question worth sitting with. If two confirmed mega-Earths have already turned up in the relatively small slice of the galaxy astronomers have carefully studied so far, using instruments that are still, in the grand scheme of things, fairly new, how many more might be waiting out there? Simple. Because nobody has pointed the right telescope at the right star yet. Every confirmed exception to an established rule tends to open the door to searching more deliberately for others like it. There is also a practical side to this discovery that rarely makes it into the headlines, but matters enormously to the scientists actually doing this work. Confirming a planet like GJ 523b is not simply a matter of pointing a telescope at a star for one night and reading off a number. It requires years of patient, overlapping observation, cross-referencing data from a space-based survey satellite, a ground-based telescope built specifically to measure the tiny gravitational wobbles of distant stars, and one of the most advanced space observatories ever built, all pointed at the same faint star roughly 130 light-years away. Every one of those instruments has its own limitations, its own sources of error, and its own blind spots. Part of why this discovery has been taken so seriously by the wider scientific community is that the same basic result, and extraordinarily, kept showing up no matter which instrument or which method researchers used to double-check it. That kind of independent confirmation matters more than people often realize when a story like this spreads quickly online. It would be easy for a single strange reading from one telescope to get exaggerated into a dramatic headline before anyone has properly checked whether the numbers hold up under closer scrutiny. That is not what happened here. The research team behind GJ 523b spent real time verifying their results before submitting them for scientific review, which is precisely why other astronomers, outside the original team, have been willing to treat this planet as a genuine, serious challenge to existing theory rather than dismissing it as a measurement error waiting to be corrected. It is also worth remembering that planet formation research rarely moves forward through single, isolated discoveries. It moves forward through patterns, built up slowly as more examples get confirmed over time. A single, unusual planet can always be written off as a strange, one-time exception, a fluke of circumstances unlikely to repeat anywhere else in the galaxy. Two confirmed examples, found using very different methods and separated by more than a decade of improving technology, start to look like something closer to a real, recognized category of planet, one that any complete theory of planet formation now has to account for, rather than quietly ignore as an outlier. So, coming back to the central question this video started with, did NASA really find a planet that changes what we believed about physics? The honest answer is more precise than that headline suggests, and honestly, more interesting than a simple yes or no. The fundamental laws of physics have not changed. Gravity still works the same way it always has. And nothing about this discovery rewrites the basic rules of the universe. What has changed is scientists' confidence in a specific working assumption. The belief that any rocky planet growing past roughly 20 Earth masses would reliably and predictably turn into a gas giant without exception. GJ 523b stands as clear, confirmed evidence that this assumption has real exceptions, and researchers are now working carefully to understand exactly why, rather than simply assuming the old model was complete. That is the real story here, and it is worth sitting with for a moment. This is not a case of scientists being proven wrong about the universe in some dramatic, embarrassing way. Why? It is science working exactly the way it is supposed to. A theory made a prediction. A new, more massive rocky planet was found that did not fit that prediction cleanly, and now researchers are doing the patient, careful work of figuring out whether the theory needs a small correction, or whether planets like this represent a genuinely different formation path that deserves its own explanation entirely, separate from the rules that govern more typical planets. Somewhere out there, 130 light years away, a dense, rocky giant is still completing its tight 18-day orbit around a small, faint star, exactly as it has been doing for the past 170 million years, long before anyone on Earth ever pointed a telescope in its direction. It does not know it has become the subject of scientific debate, or that its exact density has been calculated down to the gram by researchers working from data gathered across multiple observatories on the other side of the galaxy. It is simply doing what it has always done, quietly existing as proof that the universe still has room to surprise the people studying it, one strange, unexpected planet at a time, and very likely more waiting to be found.